No discussion of acids and bases would be complete without really talking about water. Now, water is kind of special. I'm going to talk about what's happening with it and why it's so special. So, we already talked a little bit about what the pH range is in water. So typically 0 to 14 is our pH range. In water, water does something special, which is self-dissociation. So water dissociates to form hydroxide and hydrogen ions in water. So in this, essentially, what's happening is we have two water molecules that are going to form a hydroxide and a hydrogen or hydronium ion. So if we take one water molecule, let's take a look at it. So I've got water. So here's our Lewis structure for water. And what's going to happen is that this hydrogen is going to come off as H+, and the rest of it, so notice these two electrons from this bond are going to become part of the oxygen. So they're going to come down to the oxygen, and we're going to have a hydrogen ion, and we're going to have an OH-. So we end up with OH-. So oxygen with three pairs of electrons. We have our bond, and we have the H+, because remember H+ doesn't have any electrons to it, it's just a proton. That H+ is going to attach to a separate water molecule to form H3O+. So this is how we take two water molecules and we get a hydroxide ion and we get a hydronium ion. So let's take a look a little bit more at the dissociation of water here. So we have our hydrogen and our oxygen. The hydrogen comes off, comes the hydrogen ion, we get our hydroxide ion. That hydrogen ion then attaches to water to make our hydronium ion. You may also notice that in our equation, the reaction, we have this double arrow. So this dissociation is partial. It's a weak dissociation. So this is a very weak, very, very weak electrolyte. And from that equation, we can get the Kw, so the equilibrium expression for water. So remember, it's 2H2O liquid is in equilibrium with our OH minus Q plus H3O plus AQ. We can write our K equation, so our equilibrium expression is our products, so K is going to be equal to our product, so concentration of OH minus times the concentration of H3O plus over our reactants, but H2O is a liquid here, so this is going to be over 1. So we leave that off, because normally if we have a fraction with 1 on the bottom, we just leave the 1 out. So our K expression for water is the concentration of H3O plus times the concentration of hydroxide. This is equal, so the Kw for water is 1.0 times 10 to the negative 14 at room temperature. The pKw, so the negative log of that, is going to be equal to the negative log of our Kw, so P is essentially negative log of, and it's going to be equal to 14. Now, I'm not going to get into too much about how we get from here to here, but essentially what that means is that pH, so the negative log of our hydrogen ion concentration, plus pOH is going to be equal to the pKw, or 14. So it's the negative log of 1.0 times 10 to the negative 14th is 14. So pH plus pOH is equal to 14. So pH is a measure of acidity. pOH measures basicity, so how basic something is. So if we add this pH, the measure of acidity, plus the measure of basicity, you're going to get 14. Now pH is also equal to the negative log of our OH minus concentration. And we'll get into that a little bit more when we look at bases and how we calculate with bases. But this is going to be very helpful as we deal with bases, because if we know, for example, if I know that my pOH is 10, then I know that that pH at that same solution is going to be 4. So this is just two different ways of measuring it if I'm looking at pH and pOH. So we'll take a look at what that means with our bases and how we relate pH and pOH throughout those.